Hi, everyone. So we're going to move through the rest of Chapter 9 with a couple more examples. There's a long list of homework problems in the back of Chapter 9 of the form prove or disprove without telling you which of the things are true, whether the statements are true or false. And I encourage you to look at those because that's a really good test of not just your command of this particular chapter, but of a lot of the ideas that we've had up until this point. But I'll do a few specific examples just to help you keep your wits about you. So in the previous discussion, we talked about theorems of the form, for all x of a certain type, something is true. And we showed that the negation of such a thing amounts to proving the negation of a for all statement, which means proving a there exists statement. You have to find a counterexample. The other situation is that you have a claim or a proposition, an alleged proposition of the form, there exists an x with a certain property. And to disprove that, you have to prove that that property, for all x, that property is false. So Fairmont's last theorem is one example of this. In Fairmont's last theorem, we say that there are no solutions to a particular equation. And more generally, if we have a there exists statement of the form, there exists an x in S, some set S, such that some property P of x holds, the negation of that is for all x in S, P of x does not hold. So there can't be any examples where P of x is true. So we can look at maybe something a little more concrete. This is simpler than Fermat's last theorem, but let's suppose that the claim that we're looking at is that there exists a Pythagorean triple, A, B, C, such that all of A, B, and C are odd. And the negation of this claim, if we want to disprove this, we would have to show, so first of all, we have to analyze the statement. So it says, the original claim is that there exists a Pythagorean triple with a certain property. So the negation of that is going to be for all Pythagorean triples. And if the original property was A, B, and C are all odd, or put another way, A is odd and B is odd and C is odd, then the negation of that is A is even, or B is even, or C is even. In other words, we need to show, if we're negating the original statement, we need to show that for all Pythagorean triples A, B, and C, at least one of A, B, or C is even. So let's look at how a proof of that might work. Proof of this statement. So we have a Pythagorean triple. So C squared equals A squared plus B squared. And now we want to show that at least one of A, B, or C must be even. And we can take them one at a time. So first of all, A could be even. And if A is even, then our proposition is true because one of A, B, and C is even. If A is odd and B is even, we're still okay. Because B is even. And lastly, if A and B are both odd, then A squared and B squared are odd. So C squared, which is A squared plus B squared, is even because it's a sum of odd numbers. And if c squared is even, then c is even. And how do we know that? Well, I think we've actually proved it before, but if c squared is even, I mean, maybe an easier way to say it is, if c were odd, then c squared would be odd because the product of odd numbers is odd. So using the contrapositive, if c squared is even, then c must be even. So that proves this little proposition that if you have a Pythagorean triple, at least one of the three numbers a, b, and c has to be even. Okay, another way you can often prove things don't exist is using proof by contradiction. So remember, in proof by contradiction, you assume something is true, and then you arrive at a contradictory statement, or you prove contradictory statements, and from that you conclude that the original statement must have been false. So I'm going to give, this is example 9.5 from the book, I'm going to give a slightly different proof. And the claim is that there's a real number x such that x is in the open interval from x to the fourth to x squared. This means x is bigger than x to the fourth, and x is less than x squared. That's what that means. And we're going to disprove this by contradiction. So assume that we have such an x. So the first thing we can observe here is that x is bigger than x to the fourth. So x has to be positive. Because x to the fourth is positive. I mean, it's bigger than or equal to 0 for any x, right? If you take the fourth power of x, it's got to be bigger than or equal to 0. So x is bigger than x to the fourth, and x to the fourth is bigger than or equal to 0. So x is bigger than 0. And second of all, we know that x is less than x squared. And since x is bigger than 0, we can divide both sides of this inequality by x. And therefore, we get that x is bigger than 1. On the other hand, we know that x to the fourth is less than x. So we can divide both sides of this inequality by x. Remember, x is positive. So we get x cubed is less than 1. And therefore, x cubed minus 1 is less than 0. And we can factor this left-hand side here. This is of the form x minus 1 times x squared plus x plus 1. And that's supposed to be less than 0. Well, this right here is obviously bigger than 0 because x is bigger than 0. And if the product of these two numbers is negative and this is positive, this better be negative. And therefore, we've proved that x is less than 1. And now we have a problem, because we've proved x is bigger than 1, and we've proved x is less than 1. So we've actually shown that if x belongs to the interval from x to the fourth to x squared, this implies x is bigger than 1 and x is less than 1. And recall, the idea behind proof by contradiction is that if you have a valid implication, which is what this is, and the conclusion is false, which it obviously is, this is obviously false, then the hypothesis must have been false. And so we've proved that actually there is no x that satisfies these inequalities, which is what the disproof of the claim actually said. So if you look, this is a variation on what's done in the book in example 9.5. Okay, we'll stop there and I'll let you think about some of the examples in chapter 9.